In this video, we want to take a good look on how you start to solve quadratic equations. And what you find is that there's not one way to do it, but actually four. So we're going to cover the principle of zero products, the principle of square roots, then get into completing the square, and finally, one that most people are familiar with, using the quadratic formula. Now, after we have all of that information, we'll also take a look at some quadratic equations that aren't quite quadratic, but actually with a little bit of work you can solve them using some of these quadratic techniques. So what I like to call them is quadratic equations in disguise. And then finally, just a little bit about the discriminant of one of these quadratic equations. So what we're looking to solve here when I say quadratic equation is basically any equation that can be put into this form. Ax squared plus bx plus c is equal to 0, where the a, b, and c represent numbers, and we don't want a to be a 0. We actually want that x squared term in it in order to get a quadratic equation. Now, if we do have something written in this form, say something like 5x squared plus 2x plus 3 equals 0, then we could say that that quadratic equation is written in standard form. Now, keep in mind that we're also interested in quadratic functions. And these have a very similar definition. A quadratic function is basically of the same form, only we use our function notation at the beginning to have f of x is equal to ax squared plus bx plus c. So, really think of it as the same. Also keep in mind that we will be working to solve quadratic equations, but we will also be looking for the zeros of a quadratic function. And it's really the same problem as solving a quadratic equation in standard form. You just want to know when this will equal 0. Now, the key to either one of these definitions is recognizing which things can be written in that form and which things cannot. On this slide right here, I basically have a whole bunch of different quadratic equations. And the reason why they're all quadratic, even though some of them don't look exactly like the form I had on here, is that with a little bit of manipulation, you can make them look like that form. In fact, the first one, 5x squared plus 3x minus 4 equals 0, well, that looks exactly like the form of a quadratic equation. So we can say that that one is written in standard form. Now, the one right below it, 3 equals 2 times x plus 1 squared minus 5, well, that doesn't quite look like the definition for a quadratic equation. But you can make it look like the definition by foiling out the x plus 1 part, distributing the 2, and then moving everything over to one side. And then it, sure would look like the definition that we started with. And so with all of these examples, you can definitely write all of them in standard form. So what I really want you to notice with a quadratic equation is notice how all of them will end up with an x squared term. That's really the key to seeing if you have a quadratic or not. So let's get into that solving process. Recall that when you're trying to solve an equation, and you have more than one copy of the variable in there, that you really have to get both of those variables together before you can ever really isolate it. Now, what makes this a little bit more difficult with quadratic equations is that you definitely have more than one copy usually running around, and that one of these copies of the variable is squared. Well, you can't really combine an x squared with an x. So we have to go over some special techniques on how you kind of get around this problem, and see ways that you might be able to combine them, or maybe even ways where you don't even need to. But let's first start off with some nice cases. In this first case, imagine that I want to solve the quadratic equation. 0 equals the quantity x minus 3 times the quantity x plus 5. In a case like this, I'm looking for what the value of x has to be. And since I want to know when it equals 0, you could try plugging in numbers like 3 or negative 5, and watch what happens when you do that. If you plug in a 3, the first quantity becomes 0, and 0 times anything, you get 0. If you plug in a negative 5 into the second quantity, you would have negative 5 plus 5, and that part would equal 0. So either one of those two numbers would make that particular quantity 0 and zero out the entire equation. This idea can be packaged up as the principle of zero products. And what that principle says is that if you have two numbers being multiplied together, and you know that the result is 0, then one of the numbers must be a 0. And so each of the quantities here, say the first one or the second one, is playing the role of one of those numbers. And we know that when we multiply these two quantities together, we get an answer of 0. So it says either the first quantity is 0 or the second quantity is 0. So here's how we can apply this to solve some quadratic equations. If we have a quadratic equation and we can factor it down into two pieces like this, then we can take each of those pieces and set them equal to 0. That's what the principle is allowing us to do. Now with each of these individual pieces, then you solve them for x, which is pretty nice because in each of the individual pieces we only have one x to worry about. So maybe on the one on the left, I would add 3 to both sides and get that 3 is equal to x. And then for the one on the right, I would subtract 5 from both sides and get that negative 5 is equal to x. So these are our two solutions for our quadratic equation. Let's give that technique one more try with this quadratic equation. 2x squared minus x is equal to 3. Now remember, in order to use this principle, we want to factor it into two different quantities. And we want to make sure that these two quantities, when they're multiplied together, actually equal 0. So what you would do with this one is first subtract the 3 from both sides, giving you 2x squared minus x minus 3. And then you would factor that so that you have two pieces. So I've already gone through the trouble of factoring it. And I got x plus 1 times 2x minus 3 is all equal to 0. Now it's important to have these factored pieces because then I could set each of the pieces to 0 and solve each of these separate pieces just for x. So I'd get an answer like x equals negative 1 on the left side. And let's see, on the right side I'd have to do a little bit more work, say add 3 and then divide by 2. But I'd get an answer over there like x equals 3 divided by 2. The principle of zero products is a very handy principle as long as you can factor your quadratic equation. Now in this example, you'll notice that sometimes we don't even have to factor. Something like x squared equals 64 is pretty simple to solve directly. And what I mean by directly is if you take the square root of both sides of this equation. You could see that x is equal to a positive 8 or even a negative 8. Well, the idea of solving it directly like that is the idea for the principle of square roots. That if you have x squared equals a number, that you get two answers. One where it's the square root of that number, and one where it's the negative square root of that number. Let's give that idea a try in this example. 2x squared minus 5 is equal to 5. And notice how this one only has a single x squared, so it's set up perfectly for using something like the principle of square roots. In order to solve this one, I'm going to try and isolate the x squared part and then use the principle. So in my first step, I'll add 5 to both sides and then divide by 2. So this will give me x squared is equal to 5. And then according to the principle, when I take the square root of both sides, I'll get x is equal to a positive square root of 5 and x is equal to a negative square root of 5. So you can see from those two methods, we get a lot of tools for just solving these quadratic equations, and they're not too bad. The only problem is, these two methods are only great if you could factor the quadratic equation, or if there's only a single x squared and you can do it directly. Unfortunately, not all quadratic equations fall into one of those two categories. After all, take a look at this one. 2x squared minus 1 is equal to 3x. If you move everything over to one side and try and factor it, it doesn't factor. And I not only have an x squared, I have an x. So I can't try and isolate it directly. So for something like this, we have to pick up another technique on how to solve it. This is the technique of completing the square, and it's a very special technique because it will actually allow us to get the x's together. Here are the steps that we're going to run through. Basically, you want to take the parts that have your variable, or have the x associated with it, and put them on one side. Then go ahead and check your x squared term to see if it has any coefficients in front. If it does, divide your entire equation by that coefficient. That way you just have a single x squared term with nothing out front, or you can consider it a 1. Then we're going to work to find a magic number to add to both sides so that we can actually factor it. Now the way you find this number is you take the coefficient in front of the linear term, that's the one with just x, you divide it by 2 and you square it. So when we find that number, we're going to add it to both sides. Now in doing that, we'll be able to factor the resulting equation very nicely. And once it factors, we'll only have a single x. And so with a single x, we'll use that with the principle of square roots and solve directly. Now, you can see that in this method, there are lots of steps to go through, so try and follow together carefully, and if you have to, go back over this part a few times so you can see all of the steps in action. But, let's go ahead and give this a try. So, in this example, I want to solve 2x squared plus 4x minus 2 equals 0. And this one, you could probably solve it easier just by factoring, but I really want to show you how the completing the square method works with something that's not too ugly. In my first step, what I'm going to do is start to collect things that have an x together. So if it has an x, I put it on the left side, and if it doesn't have an x, like that minus 2, I'm going to move it to the right, so add 2 to both sides. Now, that's just the first step. I'm just kind of cleaning things up a bit. In the second step, I want to check my x squared and see if it has any coefficient out front. In this example, I have a 2 in front of my x squared. So I'm going to divide everything through by a 2. That's going to make things a little bit smaller. So x squared plus 2x is equal to 1. Now for this next step, I'm going to work to find my magic number. And really that's just the name I give it. But when I start using this magic number, it's going to make the steps basically factor nicely. So watch this. I'm going to take the number in front of the linear term. So that's the 2 in front of the x. I'm going to take it and divide it by 2. So 2 divided by 2. And with that result, I'm going to square it. So 2 divided by 2, square that, and I get an answer of 1. So this 1 is what I would consider my magic number. Now I'm going to take the 1 and add it to both sides of the equation. And it may seem weird, why am I doing that? Why am I adding 1? But watch what happens on the left side of this equation now. With that 1 in there, this will factor nicely. And when I mean nicely, I mean it'll factor into x plus 1 and another x plus 1. Those factors will always be the same if you've done this correctly. And since they are the same, you can package them together as x plus 1 quantity squared. And so rather than dealing with 2 x's, I only have 1. Now since we only have 1 x at this step, that means I can start working to solve it directly. So let's get that x all alone. I'm going to take the square root of both sides. So I'll have a positive and a negative square root, and that comes from the principle of square roots. And then I'll subtract 1 from both sides. So x equals a negative 1 plus the square root of 2, and x equals negative 1 minus the square root of 2. Two different answers. So you can see that this method, even though it has a lot of steps in it, really takes advantage of factoring and the square root property. It really puts the two together. Now, completing the square is an awesome method, but unfortunately it's not always that clean. In this next example, things are going to get a little bit messier as I start to work with fractions. So watch what happens to the steps here. I have 2x squared minus 1 is equal to 3x. And in my first step, I want to get my x's on one side, and if it doesn't have an x, put it on the other. So this will give me, let's see, if I subtract a 3x from both sides, let's see, 2x squared minus 3x, and add 1 to both sides. So 2x squared minus 3x equals 1. There we go. So that was step 1. Step 2, check your x squared term, see if there's any number in front. This one has a 2, so I need to divide everything by 2. Now there's where the fractions come into play. Because if you take a 3 and divide it by 2, you got 3 halves. And if you take a 1 divided by 2, you get 1 half. Now that's okay. It just means that as we continue to do the rest of the steps, we'll have to be extra careful with those fractions. Alright, so the next step, we need to find our magic number. So I'm looking at the linear term, the minus 3 halves x, and I need to take that, divide it by 2, and square it. So let's do that. I'm going to take negative 3 halves, divide it by 2, and square it. When you divide it by 2, you get a negative 3/4. And when you square that, you get a 9/16. Now remember, that guy is our magic number. We need to add it to both sides. So let's go ahead and do that. Now this definitely looks a lot messier. X squared minus 3 halves x plus 9/16 equals 1 half plus 9/16. Well, that's okay. We can deal with fractions. And even though it doesn't look very nice, the left side is going to factor very nicely. In fact, the left side factors into x minus 3/4, the entire quantity squared. And if you're ever having problems with that part, figuring out what it will factor into, you can always figure out the number part, the x minus 3/4, because you come along, you find it when you're finding the magic number. Notice how when I took the linear term and divided it by 2, it was also a negative 3/4. And that's always going to happen. Anyway, let's see what we got here. Okay, so I have a single x, and now I'm just working to isolate it. So take the square root of both sides, and then add 3/4 to both sides. So here we have basically two solutions, that x is equal to the square root of 17 divided by 16 plus 3/4, and that x is equal to the negative square root of 17/16 plus 3/4. Now you definitely want to take this even a little bit further and simplify those roots. For example, the square root of 17 over 16 could simplify into the square root of 17 divided by 4. And so you definitely want to continue simplifying your answers. But this is just how this completing the square part works into finding those answers. Now, the most important thing about, say, something like completing the square is why anyone would want to go through all of those steps in the first place. Well, a great advantage to completing the square is that it can work with any quadratic equation. Whether it's factorable or whether there's only a single x, you can always run through those steps and come up with your solutions. Of course, the downside is a pretty big one. The completing the square process has lots of steps in it, and it's really easy to make a small mistake along the way. Well, you might be interested, is there some way that we could package up all of these steps into a handy formula? That way we don't necessarily have to memorize all the steps as we go along. And the good news is, yes, there is a handy formula that does package up all of completing the square. And that's the idea of the quadratic formula. That, say you had to start with a general quadratic equation, ax squared plus bx plus c equals 0, and maybe just use completing the square on that guy. Your result, the two answers you would get, would be x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. You get the quadratic formula. And since this is a generalization of completing the square, it has all of the advantages of completing the square. You can use this formula to solve any quadratic equation. So of course many people do like using the quadratic formula to solve these equations because it does work so nicely. But here are some quick tips when using this formula. First, you have to make sure that your equation is written in the proper form. This means you should have it equal to 0. So, have 0 on one side. Also, you have to correctly identify all the parameters needed in the formula. So what is the a, b, and c? And if there's any signs included with these numbers, make sure you take them as well. So if you have a negative 5x squared, then the a value would be the negative 5. Okay, so don't just take the 5. Well, let's go ahead and give this last method a try in order to solve 2x plus 3x squared equals 7. Now remember, in my tips, we want to make sure that this is equal to 0. So one of the first things I'm going to do is basically move everything over to one side by subtracting a 7, and then I'm going to organize it in descending power. So this means I want my x squared term, followed by the x term, followed by the constant term. So 3x squared plus 2x minus 7. When it's written like this, it's much easier to pull out what my a, b, and c values are. So the a is in front of x squared, b is in front of x, and c is the constant term, negative 7. And once you have a, b, and c, you can take all of these values and plug them into the quadratic formula. So it's negative the value of b, plus or minus the square root, the value of b squared, minus 4 times a times c, all over 2 times a. And notice how I'm taking the signs if I have any. So c was a negative 7, and I put a negative 7 directly into the formula. Now, from here, it's just a matter of simplifying, and you do want to be very careful in that process. So maybe work on the inside of that square root, maybe square the 2, and then maybe work on multiplying the 4, the 3, and the negative 7 together. If you do that, you would get negative 2 plus or minus the square root of 4 plus 84, all divided by 6. Okay, simplify this a little bit more, and maybe put together the root, and then maybe even simplify the root into something like 4 times 22, and then take the square root of that 4. Because in doing so, you get minus 2 plus or minus 2 times the square root of 22 all over 6. And then what you could do is you could cancel out that extra 2 to get the final answer I have here on the screen. And so you can see that the quadratic formula can get us to that answer very quickly, but you do have to be very careful on how you simplify. Now that you know about the quadratic formula, and you know that it always works, you might be wondering, well, why did we need all those other techniques? Well, they do have some important features in them. First, if you can recognize a quadratic equation is in one of those particularly nice forms, you might not need to have to bring up the quadratic formula in the first place. It might be faster to solve it using factoring, or maybe even faster to just try and solve it directly and take the square root. It's also important to understand those other forms to understand how the quadratic formula is built. Oftentimes, we just take this formula at face value without really realizing how much work goes into it. And also, lastly, the method of completing the square will be extremely useful when we get to the section on conics. So if you know it now, you'll be that much farther ahead when we get to that section. Because in that section, we'll use completing the square in order to manipulate certain equations and expressions and get them in a much nicer form. So now that you know about the techniques for solving quadratic equation, I'm going to show you a few other equations that aren't quite quadratic, but that you can still use some of these techniques in order to solve. And the idea is that we're going to be using some sort of substitution in order to turn it into something much more manageable. So an example would be something like x to the fourth power minus 5x squared plus 4 equals 0. So you can definitely see that that one's not quadratic because it has the x to the fourth. But what you'll see is that with a substitution, I can turn it into something that is quadratic and then use my techniques. So let's give it a try. In order to make this look more like a quadratic equation, I need to swap out the x to the fourth with something that is squared. So what I'm going to do is call another variable, u, and set it equal to x squared. So u equals x squared. Now, why am I doing that? Well, I'm basically going to start swapping other things out. I can replace the x to the fourth with a u squared and the x squared with a single u. And if you're wondering, wait, how did you swap out the x to the fourth? Well, look at our expression u equals x squared and imagine squaring both sides of that. You get u squared equals x to the fourth. So, that part is what allows you to swap out the first term. Now, when you're looking at this, u squared minus 5u plus 4 equals 0, that is definitely quadratic in terms of u. So you can use one of your 4 techniques in order to solve this guy. And I just went ahead and I factored it since it seemed to be the fastest. And that gave me a solution for basically 2 values of u, that u is equal to 1 or u is equal to 4. Now that's not quite where we stop with our answer. We actually go back and we put in our x's. So since u is equal to x squared, I would say that x squared is equal to 1 or x squared is equal to 4. And then I would use the principle of square roots to take it to that last step. So taking the square root of everything, I can get that x equals positive 1, x equals negative 1, x equals 2, or x equals negative 2. And so this would represent my 4 solutions for the original equation. Another thing to keep in mind when you're solving some of these quadratic equations is that your solutions may be imaginary. And a quick example that I could give you of that is x squared plus 1 is equal to 0. If you try and solve that directly, you would subtract 1 from both sides and then take the square root. And notice how when you take the square root of a negative, well, there's our imaginary number right there. So we'd get a solution like x equals plus or minus I. So, just be on the watch out for those when you're using any of these techniques. Now, as long as it's possible to get imaginary solutions out of these quadratic equations, you might be just a little bit curious as to when you can expect imaginary solutions or when those solutions are going to be completely real. Well, fortunately, there's a quick test that you can give an equation just to see what kind of answers it will have. And this is known as testing the discriminant. The discriminant is the part underneath the square root in the quadratic formula, so the b squared minus 4ac part. And depending on what the value of that is, the discriminant, it will tell you what your solutions will look like. So if you say compute the value of b squared minus 4ac and it equals 0, that means you will get one real answer. If, however, you do the discriminant, b squared minus 4ac, and you get some sort of positive number, then you know that you'll have 2 solutions and they'll be real solutions. And lastly, if you do the discriminant and it's a negative number, that's how you know when you will have imaginary solutions for the solutions of your entire equation. Now, an interesting thing about those solutions is they will be complex conjugates of one another. So, they're pretty much the same, just different on the imaginary part. And that's how you can tell what kind of solutions you'll get out of these quadratic equations.